In a land deep within the tunnels of MIT lived 5 engineers who said goodbye to a semester of sleep to bring their shared vision of autonomy to life. They crafted this vision in a little robot named Carl. Carl was born in a simulation, trained on algorithms to follow walls, to create desired paths, to avoid artificial objects so that one day, Carl could be brought into this world. This transition was not an easy one. He suffered many bruises and broken axles, but due to the love of his creators, he was prepared for one of the fiercest, most talked about competitions at MIT. Carl and his fellow robots only had 2 weeks to train for the autonomous race and the final challenge. For our final challenge, we chose to tackle advanced technical maneuvers. The Advanced Technical Maneuvers Challenge brings together many of the lessons we learned throughout the semester, such as simultaneous localization and mapping, real-time path planning and pursuit, advanced controls, and last but not least, computer vision. The first component of the challenge was acceleration. The goal was to autonomously drive between the walls and park within a box of cones as quickly as possible. We applied a linear regression to our LiDAR data to infer the position of the wall so that a robot could drive in parallel to it. Once Carl detects the cones to be within a certain distance, our parking controller overrides our wall following controller. Our cone detection module first converted the image frame into hue saturation values so that a color threshold could be applied. We then eroded and dilated the image to remove outliers. This gave us a cone we could find the contours of. Finally, these contours are translated into our bounding box. A homography matrix converts the pixel coordinates of the center of the bounding box to the real-world coordinates. These real-world coordinates are fed into the PD parking controller to output the new steering angle. The robot travels at a constant speed up until it reaches a specified parking distance. The robot then drifts into the center of the 4 cones. The second challenge of technical maneuvers, skid pad, takes place on a figure-8 shaped course with separate entry and exit lanes. To complete it, the car must go around the right loop twice, the left loop twice, and then park in the box marked by the 4 cones. Using Google Cartographer, we simultaneously generated a map of the course while localizing within it. We then used a Monte Carlo localization technique called particle filter to localize in the map we generated. The figure-8 path is quite feature-sparse, so we had to rely much more on our odometry measurements than we typically do. Now that we have our location, we can execute our desired trajectory with a controller called Pure Pursuit. In Pure Pursuit, the robot has something called a look-ahead length. The point on the trajectory path that intersects with a circle of a radius of this length is called the look-ahead point. The robot always drives in the direction of the updated look-ahead point, keeping in line with the desired path. We leveraged the VESC autonomous control mux to have Carl switch from Pure Pursuit to the parking controller described earlier when it was time to park. Carl achieved the fastest times for both technical maneuver challenges, completing the skid pad in 31.1 seconds and acceleration in 9.65. Carl came such a long way this semester. As you can see here, he eventually surpassed our own fitness abilities. On competition day, Carl autonomously raced through the tunnels of Stata, completing the course in 38 seconds. Thanks for joining us on the adventures of Carl. We truly had a blast exploring the future of automation. You might ask, what is the future of the field? Or more importantly, what is the future of Carl? Find out more at our team's website. This project was brought to you by Priscilla, Bouke, Alex, Dimitris, Loewen, and don't forget, Carl. Thanks for watching.